Hello, in this lecture we answer two questions. In the first question we find out the area of this rectangle ABCD, and in the second question we find out the area of this green shape that is inside square ABCD. So we start with the first question. In the drawing we have rectangle ABCD. Inside this rectangle we have this semicircle. This is called AP, that is equals to 6 units in its length. This is called slice segment PC, that is equals to 5 units. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside a rectangle are right angles, so those 4 angles they are all right angles. So okay, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. The next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. And we define the point of tendency of tangent DC with this semicircle. This point is point M. And we join points. First of all, point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, always the radius of this semicircle is equal to x units in its length according to our definition. Likewise, OE is also the radius of this semicircle that is equal to x. We join points O and M together by a straight line. OM is of course the radius of this semicircle that is equal to x. And because of the fact that the radius OM that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever your radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, you can deduce the small quadrilateral BMOA. Inside this small quadrilateral BMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. So inside this quadrilateral BMOA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral BMOA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMOA, side MO must be equal to the opposite side DA. But MO is x, therefore the opposite side DA must be also equal to x units in its length. The opposite sides in the big rectangle ABCD, the opposite sides must be also equal to each other. So in rectangle ABCD, side DA must be equal to the opposite side CB, but DA is x, therefore the opposite side CB must be also equal to x. In the next step, we join points E and P together by a straight line. By joining points E and P, we created peripheral angle APE. This is peripheral angle APE. that subtend on AE, that the diameter of this semicircle, and we know that according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, this peripheral angle APE must be equal to 90 degrees. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing we have a circle. Inside this circle we have chord AB, that is the diameter of the circle, and we also have this is peripheral angle ACB that subtends on AB, that is the diameter of the circle, and therefore according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. We have already implemented rule 7 in our drawing. We have peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its side. Therefore, peripheral angle APE is a right angle according to rule 7. Okay, in the next step we define this angle as alpha. So in the right angle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first base angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first base angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we prove that the right big triangle ABC is similar to this right small triangle APE. So why those two right angles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to the small right triangle AP. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to this angle A as it belongs to the right big triangle ABC, it will be defined as angle CAB. And angle A equals to itself. So if we relate to angle A as it belongs to the right small triangle APE, it will be defined as angle PAE. So repeat again. This equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle ABC. In the right big triangle ABC, and it is equal to this angle, this is actually angle APE, the right small triangle APE. Repeat again, I shall find out that angle ABC in the right big triangle ABC equals to angle APE, in the small right triangle APE, they are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on sulfur, therefore they are equal to each other. So actually, this is angle ACB, in the right big triangle ABC, and it is equal to this angle. This is actually angle PEA, in the right small triangle APE. So repeat again. Actually found out that angle ACB in the right big triangle ABC equals to angle PEA in the right small triangle APE. They are both equal to 90 degrees on sulfur, therefore they are equal to each other. So we actually found out that all the figures of the right big triangle ABC are correspondingly equal to all the figures of this right small triangle APE. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that the right big triangle ABC is similar, this is the sign of similar, to the right small triangle APE according to angle similarity rule. And for the fact that the right big triangle ABC is similar to the right small triangle APE, we will derive that the following relationship exists between their sides. We will derive that side AP of the right small triangle APE over side AB of the right big triangle ABC is equal to side AE of the right small triangle APE over side AC of the right big triangle ABC. So repeat again. We will derive that side AP of the right small triangle APE over side AB of the right big triangle ABC equals to side AE of the right small triangle APE over side AC of the right big triangle ABC. AP equals to 6 units in its length according to what is given as the question. Over AB. AB is the missing side, so we leave it as it is. And it is equal to AE. AE is the diameter of this semicircle, that is equal to 2x. Over AC. AC in total equals to 6 plus 5, that is 11. So in total, we found out that 6 over AB equals to 2x over 11. Here we will cross multiply this equation, and we get that 6 times 11 is 66, and it is equal to 2x times AB. So in total, we found out that 66 equals to 2x times AB. Here we divide this equation by 2, and we get that 66 over 2 is 33, and it is equal to 2x over x is x. So in total, this expression equals to x times AB. So in total, we found out that 33 equals to x times AB. Here we divide this equation by x, and we get that AB equals to 33 over x units in its length. Again, I shall find out that the length of this side AB of rectangle ABCD is equal to 33 over x units. Our mission is to find out the area of this rectangle ABCD. So we have to find out the area of rectangle ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is CB. AB equals to 33 over x, and CB equals to x. So in total, if we found out that the area of rectangle ABCD equals to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So in total, if we found out the area of this rectangle ABCD is equal to 33 square units. So the area of rectangle ABCD is equal to 33 square units. And that is the answer to the question. Repeat again, the area of this rectangle ABCD is equal to 33 square units. So we finish with the first question. The next step, I present to you the second question, and we solve the second question of this lecture. Our mission, this is the second question, is to find out the area of this green shape. So in the drawing we have square ABCD, and we know that this is line segment BP, that is equal to line segment PC, and we also know that this is triangle OPC, that is equal to 5 square units in its size, and our mission is to find out the area of this green shape. So first of all, we define the length of this line segment BP as A, and because of the fact that BP equals to PC according to what is given as the question, so if BP is A, then PC must be also equal to A. So BC in total equals to A plus A, that is 2A, and we know that all the sides of any square are equal to each other. Therefore, side AD of square ABCD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this vertex angles as theta, then this angle must be also equal to theta because they are equal to each other. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles, and they are located between the parallel lines AD and BC, and therefore they are equal to each other according to rule 15. According to rule 15, alternating angles between parallel lines are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to rule 15. Likewise, those two angles are also defined as alternating angles, and they are located between the same parallel lines AD and BC, therefore they are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to rule 15. So in total, if we found out that those two triangles are similar to each other according to angle similarity rule. Why? Because, in total, if we found out that those two triangles are similar to each other according to angle similarity rule. Why? Because, in total, if we found out that those two triangles are similar to each other according to angle similarity rule. Why? Because, in total, if we found out that those two triangles are similar to each other according to angle similarity rule. Why? Because In both triangles we have angle theta, in both triangles we have angle alpha, and in both triangles we have angle beta. Therefore, those two triangles are similar to each other according to angle similarity rule. So write it down. So if we found out that the big triangle AOD is similar, this is a sign of similar, to the small triangle COP according to angle similarity rule. So in the next step I will present to you a new rule that relates to two similar triangles, and we will implement the new rule in our two similar triangles, triangle AOD and triangle POC. The new rule is rule 22. So according to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have those two triangles that are similar to each other. That is to say, this triangle ABC is similar to this triangle DEF. And according to this rule 22, the ratio between the areas of those two triangles, what is the ratio of the areas of those two similar triangles? It is actually the area of triangle ABC over the area of this triangle EDF. That ratio, according to this rule 22, this ratio is equal to the square of the ratio of their corresponding sides. So what is the square of the ratio of their corresponding sides? In those two triangles, side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF, and finally, side CB is the corresponding side of side EF. So, we have side AC, it is the corresponding side of side DF. So, what is the square of the ratio of those two corresponding sides? It is of course AC over DE squared. So, the ratio between the areas of the two similar triangles is equal to the square of the ratio between their corresponding sides. Likewise, side AB is the corresponding side of side DF. So what is the square of the ratio of those two corresponding sides? It is of course AB over DF squared. So the ratio between the areas of the two similar triangles is equal to the square of the ratio of their corresponding sides. This is AB over DF squared. And finally, side CB is the corresponding side of side CF. So what is the square of the ratio of those two corresponding sides? It is of course CB over EF squared. CB over EF squared. So the ratio between the areas of those two similar triangles is equal to the square of the ratio between their corresponding sides. It is actually CB over EF squared. Okay, so I can actually implement the new rule 22 in our two similar triangles. We already found out that this big triangle ADO is similar to this small triangle, triangle COP. So according to rule 22, the ratio between the areas of those two similar triangles, what is the ratio between the areas of those two similar triangles? It is of course the area of triangle ADO over the area of triangle COP. The area of triangle ADO over the area of triangle COP is the ratio between the areas of those two similar triangles, and that ratio is equal to the square of the ratio of those two, the square of the ratio of their corresponding sides. In these two similar triangles, side AD is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is in front of this angle theta, and in this small triangle, side PC is also in front of this angle theta. Therefore, side AD is the corresponding side of side PC. And the square of the ratio of those two corresponding sides is, of course, AD over PC squared. AD over PC squared. So, according to rule 22, the ratio between the areas of the two similar triangles is equal to the square of the ratio of their corresponding sides. So this equation is the implementation of rule 22 in our drawing. The area of triangle ADO, the area of this big triangle, is unknown, so we leave it as it is. The area of triangle ADO over the area of the small triangle COP. The area of this small triangle COP is 5 square units according to what is given as the question. So we substitute the area of triangle COP by 5, and it is equal to AD over PC squared. AD is 2A over PC. PC is A squared. We have A in the denominator and A in the denominator, so A will get cancelled, and we have only with 2 squared, that is 4. So today we should find out that the area of the big triangle ADO over 5 is equal to 4. Here we multiply this equation by 5, and we get that the area of the big triangle ADO, the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. So I should find out that the area of this big triangle ADO is equal to 20 square units. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of this big triangle ADO over side PC of this small triangle POC is equal to side AO of this big right triangle ADO over side OC of this small triangle POC. So I write it down. Side AD of the big right triangle ADO over side PC of the small right triangle PCO is equal to side AO of the big right triangle AOD over side OC of the small right triangle POC. AD is 2A over PC. PC is A, and it is equal to AO over OC. In this side of the equation we have A in the denominator and A in the denominator, so A will get cancelled and we are left only with 2. So we found out that 2 equals to AO over OC. Here we multiply this equation by OC and we get that 2 times OC is equal to AO. And again, 2 times OC equals to AO. We define the length of side OC as B. That is to say, OC equals to B units in its length according to our definition. And we substitute OC in this equation by B, and we get that 2B equals to AO. So if we found out that if the length of this side OB is B, then the length of this side AO is 2B. That is to say, side AO is twice as long as side OC. Okay. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. the new rule is rule 23. Rule 23 is true in any triangle, so this is triangle ABC that could be any triangle. In this triangle ABC, if you draw the red line segment AP, it will divide this triangle ABC into two smaller triangles. The first triangle is triangle APB, and the second triangle is triangle APC. This rule 23 is about those two small triangles that were created by drawing line segment AP in triangle ABC. Okay, so and according to this rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. So what is the ratio between the areas of those two small triangles? It is actually the area of this triangle APC over the area of this triangle. It is the area of this triangle ABP over the area of this triangle APC. Again, it is the area of triangle ABP over the area of triangle APC. What is the area of this triangle ABP? It is equal to the base, that is BC, times the height, that is edge, over 2. And again, the area of this triangle ABP is equal to the base BP times the height edge over 2. Likewise, the area of this triangle APC it is equal to the base PC times the height edge over 2. The base PC times the height edge over 2. In both triangles, we have the same height, that is edge. And the ratio between the areas of those two small triangles is, of course, it is the area of triangle ABP, that is BP times edge over 2, over the area of triangle ABC, that is CP times edge over 2. So this expression is the ratio between the areas of those two small triangles. So in this expression, we have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. We have also edge in the numerator and edge in the denominator, so edge also gets cancelled, and we are left only with BP over CP. BP over CP. BP is the base of this triangle ABP, and PC is the base of this triangle APC. So in total, we should find out that the ratio between the areas of those two triangles, that is actually triangle ABP over triangle APC, equals to the ratio between their bases. That is to say, it is BP over PC. BP over PC. Again, the ratio between the areas of those two small triangles, that is actually the area of triangle BP over the triangle APC, is equal to the ratio between their bases, that is actually BP over CP. So I can actually implement rule 23 in our drawing. Why put in our drawing? We have the big right triangle ADC. This is the big right triangle ADC. This is line segment OD that divides the right triangle ADC into two parts, or into two smaller triangles. The first small triangle is triangle ADO, and the second small triangle is triangle ODC. So all the requirements of rule 23 are satisfied, and therefore we can implement here rule 23. According to rule 23, the ratio between the areas of those two triangles, what is the ratio between the areas of those two small triangles? It is actually the area of triangle ADO it is the area of triangle ADO over there of this small triangle ODC. Repeat again. The ratio between the areas of those two small triangles is actually the area of triangle ADO over the area of triangle ODC. That ratio is equal to the ratio between their corresponding bases. The base of this triangle ADO is AO, and the base of this triangle OCD is OC. So the ratio between their corresponding bases is AO over OC. So this equation is the implementation of rule 23 in our drawing. Repeat again, the ratio between the areas of those two small triangles is the area of triangle ADO over the area of triangle OGC, and that ratio is equal to the ratio between their corresponding bases. That is to say, it is AO over OC. The area of this triangle ADO is 20, so let's substitute the area of triangle ADO by 20 over the area of this triangle OGC. The area of this triangle OGC is unknown, so we leave it as it is. The area of triangle OGC is equal to AO over OC. AO is 2B and OC is B. So in total, we should find out that 20 over the area of triangle OGC equals to 2B over B. We have B in the denominator and B in the denominator, so B will get cancelled and we are left only with 2. So in total, we should find out that 20 over the area of triangle OGC is equal to 2. Here we multiply this equation by the area of triangle OGC, and we get that 20 equals to 2 times the area of the small triangle OGC. So here we will divide this equation by 2, and we get that the area of the small triangle OGC is equal to 20 over 2, that is 10 square units. So we should find out that the area of this small triangle OGC is equal to 10 square units. It is very easy to see from the drawing that the area that this right triangle ABC can go to the right triangle ADC, that those two triangles can go into each other according to side rule. That is to say, side AB of this triangle ABC is equal to side DC of this right triangle ADC, because ABCD is a square. Likewise, side AD, side BC of triangle ABC is equal to side AD of triangle ADC for the same reason, and side AC is a common side that belongs to both triangles. That is to say, AC equals to itself is a common side that belongs to both triangles. So in total, we can find out that those two right triangles, triangle ABC and triangle ADC, can go into each other according to side rule. So I write it down. I shall find out that the right big triangle, triangle ABC, congruent, this is the sign of congruent, to the right triangle ADC, according to side rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. Whenever you have two triangles that can go into each other, they must also have the same areas. But the area of this triangle ADC, it is very easy to see from the drawing that the area of this triangle ADC in total is equal to 20 plus 10, that is 30 square units. So you can write here that the area of this triangle ADC is equal to 30 square units. And from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30. We derive that the area of triangle ABC is also equal to 30 square units from one side, but from the other side, what is the from this triangle ABC. Actually, it is very easy to see from the drawing that the area of this right triangle ABC it is equal to the green area plus the area of this triangle POC. So if we define the side of this green area as x, that is to say, the green area is equal to x square unit in its size according to our definition. So in total, the area of this big right triangle ABC will be equal to x plus 5 square units from the other side. So from the other side, the area of triangle ABC is also equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We'll derive that x plus 5 equals to 30. So here we subtract 5 from this equation, and we get that x equals to 30 minus 5 is 25. So in total, we should find out that x, that is the area of this green shape, is equal to 25 square units. So the answer to the question is that the area of this green shape is equal to 25 square units. Okay, it is equal to 25 square units. And that is the answer to the second question. So we finish with the second question. In the next step, as far as the lecture, we'll start with the first question, of course. Our mission in the first question is to find out the area of this rectangle ABCD. So in the drawing we have a rectangle ABCD. Inside this rectangle we have this semicircle. In addition, we know that this is chord P8, that is equal to 6 units in its length. This is line segment PC, that is equal to 5 units. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those 4 angles inside rectangle ABCD are right angles. We define the center of this semicircle, this point is point O. We define the radius of this semicircle as x. Point O is the center of this semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to x units in its length according to our definition. Likewise, OE is also the radius of this semicircle, is equal to x. We join points O and M together by a straight line. OM is of course the radius of this semicircle, that is equal to x. And because of the fact that the radius OM, that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we created the small quadrilateral DEOM. Inside this small quadrilateral DEOM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrilateral DMOA, we have 4 right angles. And according to rule 5, any quadrigonal that has 4 right angles must be a rectangle if not a square. So we relate to this quadrigonal, to this one quadrigonal, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DMOA, side MO must be equal to the opposite side DA. But MO is X, therefore the opposite side DA must be also equal to X units in its length. Likewise, in the big rectangle ABCD, the opposite sides are equal to each other. That is to say, side DA is equal to the opposite side CB. But DA is X, therefore the opposite side CB must be also equal to X units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we created peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle. And you know that according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its sides. Therefore, this peripheral angle APE is a right angle according to rule 7. We define this angle as alpha. So in the right angle APE, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right angle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right angle ABC is similar to this small right triangle APE. So what those two right triangles are similar to each other? First of all, this is angle A, that is the common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to this small right triangle APE. So we can find out that angle A equals to itself is a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we found out that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of this right small triangle APE, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side AP of the right small triangle APE over side AB of the right big triangle ABC is equal to side AE of the right small triangle APE over side AC of the right big triangle ABC. And again, we derive that side AP of the right small triangle APE over side AB of the right big triangle ABC equals to side AE of the right small triangle APE over side AC of the right big triangle ABC. AP 6 over AB. AB is the missing side, so we leave it as it is, and it is equals to AE. AE is the diameter of the semicircle, that is equals to 2x over AC. AC is 6 plus 5, that is 11. So in total, we found out that 6 over AB equals to 2x over 11. Here we cross multiply this equation, and when we found out that 6 times 11 is 66, and it is equals to 2x times AB. Here we divided this equation by 2, and when we found out that 66 over 2 is 33, and 2x over x is 2x over 2 is x. So in total, this expression equals to x times AB. So in total, we found out that 33 equals to x times AB. Here we divided this equation by x, and finally found out that AB equals to 33 over x units in its length. This is side AB of rectangle ABCD that is equal to 33 over x units. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, you know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is BC. So in total, the area of rectangle ABCD must be equal to the length AB times the width BC. The length AB is 33 over x, and the width CB is x. So in total, the area of rectangle ABCD must be equal to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So actually found out that the area of this rectangle ABCD, that is the area that we are looking for in this question, is equal to 33 square units. The area of the rectangle ABCD equals to 33 square units. So we finish with the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. Our mission in this second question is to find out the area of this grain shape. So in the drawing we have square ABCD, and we also know that this is line 7 BP, that is equals to line 7 PC. In addition, we know that this is triangle OPC, that is equals to 5 square units in its size. Again, our mission is to find out the area of this grain shape. So, first of all, we define the length of this line 7 BP as A. But because of the fact that BP equals to PC, PC must be also equal to A. And we also know that all the sides of any square are equal to each other. So BP in total equals to A plus A. BC in total equals to A plus A, that is 2A. Therefore, side AD of square ABCD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta, because they must be equal to each other, according to the rule that I mentioned. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles, and according to Rule 15, alternating angles between parallel lines are equal to each other. So those two alternating angles that are located between the parallel lines AD and BC must be also equal to each other according to Rule 15. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to Rule 15. Likewise, those two angles are also defined as alternating angles, and are located between the same parallel lines AD and BC. Therefore, they must be equal to each other according to Rule 15. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they are equal to each other according to Rule 15. So in total, we have found out that this big triangle ADO is similar to this small triangle OPC according to angle similar to. That is to say, in both triangles we have angle theta, in both triangles we have angle alpha, in both triangles we have angle beta. Therefore, those two triangles are similar to each other according to angle similar to. And for the fact that those two right triangles are similar to each other, we can implement here a new rule that I presented to you. So I present you the new rule again, and we'll implement the new rule in our drawing. The new rule is Rule 22. According to Rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing, we have those two triangles. This is triangle ABC, this is triangle DEF. Those two triangles are similar to each other. So according to this rule, Rule 22, the ratio between the areas of those two triangles, that is to say, the area of triangle ABC over the area of triangle EDF, that is the ratio between the areas of those two similar triangles, is equal to the square of the ratio of their corresponding sides. What is the square of the ratio of their corresponding sides? In those two triangles, side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF, and finally side CB is the corresponding side of side DF. So, side AC is the corresponding side of side DE. So the square of the ratio of those two corresponding sides is of course AC over DE squared. So in total, we have found out that the ratio between the areas of those two similar triangles, that is actually the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides. This is actually AC over DE squared. Likewise, side AB is the corresponding side of side DF, and the square of the ratio of those two corresponding sides is of course AB over DF squared. It is AB over DF squared. So the ratio between the areas of those two similar triangles, that is actually the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides, that is AB over DF squared. And finally, Side CB is the corresponding side of side EF. And the square of the ratio of those two corresponding sides is of course CB over EF squared. CB over EF squared. So in total, we have found out that the ratio between the areas of those two similar targets, that is actually the area of target ABC over the area of target EDF, is equal to the square of the ratio of their corresponding sides, that is actually CB over EF squared. So we can actually implement rule 22 in our drawing. Why? Because in our drawing we have already found out that the big triangle ADO is similar to this small triangle COP. Now we can implement here rule 22. According to rule 22, the ratio between the areas of those two similar triangles, the ratio between the areas of those two similar triangles is of course the area of triangle ADO over the area of triangle COP. That ratio is equal to the square of the ratio of their corresponding sides. What is the square of the ratio of their corresponding sides? Side AD is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is in front of angle theta in this big triangle ADO. Likewise, side PC is also in front of this angle theta in the small triangle POC. Therefore, side AD is the corresponding side of side PC. So, the ratio between the areas of those two similar triangles is equal to the square of the ratio of their corresponding sides. Side AD is the corresponding side of side PC, and the square of the ratio of those two corresponding sides is of course AD over PC squared. AD over PC squared. So in total, we should find out that according to rule 22, the ratio between the areas of the two small similar triangles, that is actually the area of triangle ADO over the area of triangle COP, is equal to the square of the ratio of their corresponding sides, that is actually AD over PC squared. So this equation is the implementation of rule 22 in our drawing. The area of triangle ADO is unknown, so we leave it as it is over the area of the small triangle COP. It is given as the equation that the area of this triangle COP is 5 square units. So we substitute the area of this triangle COP by 5, and this is equal to AD over PC squared. AD is 2A, PC is A. Again, AD is 2A and PC is A. And we have to square it. So it is 2A over A squared. According to the equation, we have to square it. So it is 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled. We have only 2 squared, that is 4. So in total, we should find out that the area of triangle ADO, the big triangle ADO over 5 equals to 4. Here we multiply this equation by 5 and found out that the area of the big triangle ADO equals to 5 times 4, that is 20. So we found out that the area of this big triangle ADO is 20 square units. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle COP is equal to side AO of the big triangle ADO over side CO of the small triangle COP. Repeat again. Side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of the big right triangle AOD over side OC of the small triangle COP. AD is 2A and PC is A. Again, AD is 2A and PC is A. So we have here 2A over A. We have A in the numerator and A in the denominator, so A gets cancelled, we left only with 2. So in total we should find out that 2 equals to AO over OC. Here we multiply this equation by OC and found out actually that 2 times OC equals to AO. We define the length of side OC as B. We substitute OC by B in this equation and we found out that 2B equals to AO. So we found out that if the length of this side OC is B, then the length of side AO must be equal to 2B. That is to say, AO is twice as long as OC. Okay, so in the next step, I presented to you a new rule and implemented a new rule in our drawing. The new rule is rule 23. According to rule 23, first of all, rule 23 is true in any triangle, so this is triangle ABC that could be any triangle. In this triangle ABC that could be any triangle, if you draw the red line segment AP, this red line segment AP we divide this triangle into two parts. We divide triangle ABC into two smaller triangles. The first triangle is triangle ABP and the second triangle is triangle APC. Rule 23 talks about those two smaller triangles that were created by drawing line segment AP in this triangle ABC. According to this rule, Rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. So the area of this line ABP is the base BP times the height edge over 2. Because again, the area of this small triangle ABP is the base BP times the height edge over 2. Likewise, the area of this triangle APC is the base PC times the height edge over 2. And the ratio between the areas of those two triangles is equal, of course, to the area of triangle ABP over the area of triangle APC. And that ratio is equal to the ratio between their corresponding bases. The base of triangle ABP is BP and the base of this triangle APC is PC. And the ratio between their bases is of course BP over PC. BP over PC. Actually, we arrived to this equation by putting those two expressions here. That is to say, the area of triangle ABP or the area of triangle ACP is the ratio between those two expressions. So we have edge in both in the numerator and also in the denominator, so edge will get cancelled. Likewise, we have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled, and we are left only with BP over CP. That is to say, in total, we found out that the ratio between the areas of those two small triangles is equal to BP over CP. That is the ratio between their corresponding bases. BP is the base of triangle ABP and PC is the base of triangle ACP. And the ratio between their bases is of course BP over CP. So in total, the ratio between the areas of those two small triangles is equal to the ratio between the corresponding bases, that is BP over CP. So we can actually implement this rule 23 in our drawing. Why? Because in our drawing we have the big right triangle ADC, and we also have this line segment OD that divides the big right triangle ADC into two small triangles. The first triangle is triangle ADO and the second triangle is triangle ODC. And Rule 23 talks about those two small triangles that were created by drawing line segment OD in triangle ADC. And according to Rule 23, the ratio between those two small triangles that were created by drawing line segment OD in triangle ADC, the ratio between those two small triangles is equal to the ratio between their corresponding bases. The base of triangle ADC is AO, and the base of this triangle ODC is OC. So in total, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. It is actually AO over OC. And again, according to Rule 23, the ratio between those two small triangles is actually the area of the small triangle AOD over the area of triangle ODC is equal to the ratio between their corresponding bases. That is actually AO over OC. AO over OC. Repeat again, the ratio between the areas of those two small triangles is actually the area of triangle AOD over the area of triangle ODC, and that ratio equals to the ratio between their corresponding bases. That is AO over OC. AO over OC. The area of triangle AOD, the area of this triangle AOD is 20. So we substitute the area of triangle AOD by 20 over the area of triangle ODC. The area of this triangle ODC is unknown, so we left it as it is. So it is 20 over the area of triangle ODC, and it is equals to OA over OC. OA is 2B and OC is B. So again, OA is 2B and OC is B. So we have B in the numerator and B in the denominator, so B will get cancelled and we left only with 2. So in total we should find out that 20 over the area of triangle ODC equals to 2. Here we multiplied this equation by the area of triangle ODC, and finally found out that 20 equals to 2 times the area of triangle ODC. Here we divided this equation by 2, and finally found out that the area of the small triangle ODC, the missing area, is equal to 20 over 2, that is 10. So she found out that the area of this small triangle ODC is equal to 10 square units. It is very easy to see from the drawing that the area of this triangle ABC, that this right triangle ABC can go into this right triangle ADC according to side rule. So why those two right triangles can go into each other? First of all, side AB of triangle ABC equals to side DC of triangle ADC because of the fact that ABCD is a square, and we know that all the sides of any square are equal to each other. Therefore, side AB of triangle ABC equal to side DC of triangle ADC. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC for the same reason. And finally, side AC is the common side that belongs to both triangles, so we can write down that side AC equals to itself is the common side that belongs to both triangles. So in total, we can found out that triangle ABC can go to triangle ADC according to side rule. Continue again. We can found out that the triangle ABC can go, this is the side of congruent to triangle ADC according to side rule. And from the fact that those two triangles can go into each other, we derive that they have also the same areas. Why? Because of the fact that any two triangles that can go into each other, they must have also the same areas. Therefore, the area of triangle ABC is equal to the area of triangle ADC. But for the drawing, it is very easy to see that the area of this triangle ADC, in total, it is equal to 20 plus 10, that is 30 square units. So we can write down here that the area of triangle ADC, it is equal to 30 square units. And for this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is equal to 30 square units. The area of triangle ABC is equal to 30 square units. That is from one side, but from the other side, the area of this triangle ABC is equal to the area of the green shape plus the area of this triangle, that is 5. So if we define the area of this green shape as x, that is to say the area of this green shape equals to x square units according to our definition, then in total the area of this triangle ABC will be equal to x plus 5, because 5 is the area of this triangle POC. So in total the area of this triangle ABC from the other side, it is equal to x plus 5 square units. So from the other side, the area of this triangle ABC is equal to the area of triangle ABC from the other side is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. X plus 5 equals to 30. Here we subtracted 5 from this equation, and finally found out that x equals to 30 minus 5, that is 25. So in total, we have found out that the area of this green shape is equals to x is equal to 25 square units. Repeat again, the area of this green shape is equal to 25 square units. Okay, thank you very much.